Before we talk about the age of the universe, it helps to slow down. There is no rush to understand everything. The universe itself did not rush. It unfolded slowly, over billions of years, and it continues to do so. So we begin in the same way, quietly. What is time? Time feels familiar to us. We measure it in seconds, minutes, hours, days. We feel it passing. But time is not as simple as it seems. Time is not something separate from the universe. Time is part of it. Without the universe, there is no time. When we ask about the age of the universe, we are really asking, how long has change been happening? How long has space been expanding? How long has energy been cooling? How long has matter been forming? Age is not just a number. It is a measure of transformation. The question of the universe's age is ancient. Long before telescopes, before mathematics, humans looked at the sky and wondered, did the universe have a beginning? Has it always existed? Will it ever end? These questions arise naturally, because we experience beginnings and endings every day. Our lives are short, a few decades, a century at most. This makes cosmic time difficult to imagine. Billions of years stretch far beyond intuition. So instead of trying to grasp it all at once, we approach it gently. One thing is clear: the universe is not static. It changes. Stars are born and die. Galaxies move. Space itself stretches. If the universe changes, then it must have a history, and a history has a length. For much of human history, many believed the universe was eternal, always existing, unchanging. But modern observations tell a different story. They show motion, expansion, evolution. And expansion suggests a past where everything was closer together. Imagine watching a video of the universe expanding, then slowly reversing it. Galaxies move closer. Space shrinks. Distances disappear. Eventually, everything converges toward a very dense state. That moment marks the beginning of cosmic time. It is important to understand something subtle. The beginning of the universe was not an explosion in space. There was no empty space waiting around. Space itself was expanding, everywhere, at once. This is difficult to picture, and that's okay. Understanding comes slowly. As space expanded, time began to flow. There was no before in the usual sense. Time itself started with the universe. This makes the age of the universe a unique concept. It is the age of time itself. We won't focus on numbers yet. Not yet. First, we build understanding. Numbers make sense only after meaning is clear. So for now, we stay with ideas and quiet reflection. The universe is not aware of observers. It does not keep time for anyone. It simply follows physical laws. Slowly, patiently. The universe does not plan. It does not aim for complexity. It follows simple rules. And complexity emerges naturally. Time allows this process. Physics is the language we use to describe how the universe changes. It does not explain why in a human sense. It explains how. And through this, we can estimate age. modern science relies on observation, not belief, not preference. We measure light. We measure motion. We measure temperature. These measurements carry information from deep time. The night sky is not just decoration. It is a record. Every point of light carries history. Some of that light began its journey long before Earth existed. Understanding the age of the universe requires patience. The story unfolds layer by layer. Nothing here is rushed. You do not need to remember everything. You do not need to stay alert. This journey is slow and calm by design. When we speak about the age of the universe, we are not describing how old something looks. We are not measuring wrinkles, or wear, or decay. The age of the universe is a measure of duration. It is the amount of time that has passed since the universe began to change. In the way we observe today, some galaxies look young, some look old, but appearance can be misleading. In the universe, age is not judged by looks. It is judged by process, by motion, by expansion, by cooling, by transformation. Time in the universe is always linked to change. If nothing changed, time would have no meaning. The age of the universe is really the length of its transformation, from a dense beginning to the vast cosmos we see now. When we say the age of the universe, we do not mean that all things are equally old. Stars are younger than the universe. Galaxies formed later. Planets appeared much later still. The universe is older than everything inside it. Think of the universe as a long story. The age of the universe is the length of that story so far. It includes an early simplicity, a gradual structure, an increasing complexity. The age is the span of this unfolding. To measure an age, we need a starting point. For the universe, this starting point is the moment when expansion began, not because it is dramatic, but because it is definable. It is the earliest moment we can meaningfully describe with physics. Science does not describe purpose or intention. It describes sequence. The age of the universe is not a statement about why the universe exists. It is a statement about how long it has been evolving. The universe did not begin in the way everyday objects begin. There was no empty space waiting, no location, no outside observer. The beginning was a condition, not an event. This is one of the most important ideas. Time did not exist before the universe. So the age of the universe is the age of time itself. This makes it different from any other age we measure. Our minds evolved to think in everyday terms. Before, after, cause, effect. But the beginning of the universe is not an everyday situation. It sits at the edge of intuition. That discomfort is normal. In science, age is determined by consistency. Different methods must agree with each other. The age of the universe is not guessed. It is inferred. from multiple independent observations. There is no single cosmic clock. Instead, there are many clocks. The expansion of space, the cooling of radiation, the evolution of stars, the formation of structure. When all these clocks point to the same time span, confidence grows. Everything we know about the universe's age comes from observation. We observe light. We observe motion. We observe temperature. The universe tells its age. Through its current state, the age of the universe is always changing. Every second that passes, the universe grows older. The number is not fixed. It is updated continuously. We exist at one moment, along a vast timeline. The present is simply the latest chapter. The age of the universe includes us, but does not depend on us. Instead of asking, "How old is the universe?" we can ask, "How long has the universe been evolving?" in the way we can observe. This shift makes the idea clearer. We still avoid numbers here. Precision comes later. First comes understanding. Numbers without meaning do not help. The universe unfolds slowly. It does not rush. Understanding it requires the same patience. Take a moment to pause. There is no need to hold these ideas tightly. Let them settle. They will return gently as we move forward. When we look at the world around us, everything feels immediate. Light from a nearby lamp reaches our eyes almost instantly. The delay is too small to notice, but over great distances, light takes time to travel. And this simple fact changes everything we know about the universe. Light does not travel infinitely fast. It moves at a fixed speed. Very fast, but not instant. Because of this, every time we look into space, we are also looking into the past. The farther away something is, the longer its light has been traveling. A nearby star is seen as it was years ago. A distant galaxy is seen as it was billions of years ago. Distance and time become linked. Space becomes a record of history. The night sky is not a snapshot of the present. It is a collection of moments, each from a different time. Some light left its source before Earth existed, some before the sun formed, some before the first stars appeared. Every point of light is a message from the past. When scientists build larger telescopes, they are not just seeing farther, they are seeing earlier. Each increase in distance pushes observation closer to the beginning of the universe. Telescopes are time machines, not because they travel through time, but because they collect ancient light. As we look farther and farther away, we eventually reach a limit. Beyond a certain distance, there are no stars, no galaxies, only faint radiation. This light comes from a time when the universe was still very young. It is one of the strongest clues to the universe's age. Nothing about this requires motion. We do not need to leave Earth. We simply collect light that has already been traveling for billions of years. The universe delivers its history to us, slowly, patiently. If we can see the universe as it was long ago, we can reconstruct its timeline. We can see earlier stages. We can compare past and present. And from that comparison, we can estimate how long change has been happening. Light carries information. Its color, its brightness, its pattern. All of these encode details about where and when it came from. By studying light carefully, scientists can read its story. As light travels through expanding space, its wavelength stretches. It shifts toward red. This shift increases with distance, and distance corresponds to time. So redshift becomes a measure of age. The farther the light has traveled, the older it is. When scientists measure redshift from many galaxies, they see a pattern. All distant galaxies show signs of moving away. All show stretched light. This consistency tells a single story. The universe has been expanding for a very long time. An important detail emerges. Every observer sees expansion. No matter where you look from, galaxies move away. This tells us there is no central point. Expansion happens everywhere. This supports the idea that space itself is changing, because expansion affects light predictably. Light becomes a clock, not a mechanical one, but a natural one. By reading this clock, scientists estimate how long expansion has been occurring. This is one way. The age of the universe is measured. The ideas here are subtle. They do not require memorization. They require patience. Understanding grows gradually, like the universe itself. When we look very far away, we see galaxies that look different, less organized, more chaotic. These galaxies are younger. They show early stages of formation. This confirms that the universe has evolved over time. The farther back we look, the simpler the universe appears. Fewer structures, less complexity. This trend supports the idea of a beginning, followed by gradual growth. Eventually, light from stars disappears. Before stars existed, there was darkness. But even that darkness left behind a trace, a faint glow, that fills all of space. This glow marks a very early time. No single observation reveals the age alone, but together, all observations agree. Light from distant galaxies, patterns in radiation, motions of space. They tell the same story. A universe that has been expanding for billions of years. You are not seeing the universe as it is now. You are seeing it as it was. Every glance upward is a look into history. This realization can feel humbling and calming. For a long time, people imagined the universe as still, unchanging. fixed in place. Stars and galaxies were thought to sit quietly in space, but careful observation revealed something else. The universe is moving, not in one direction, but in all directions at once. When astronomers began studying distant galaxies, they noticed a pattern. Almost every galaxy appeared to be moving away. The farther away a galaxy was, the faster it seemed to recede. This was not random motion. It was systematic. This is an important distinction. Galaxies are not simply flying through empty space. Instead, space itself is stretching. As space stretches, the distance between galaxies increases. They move apart, without traveling anywhere locally. No matter where you observe from, the same pattern appears. All distant galaxies are moving away. This means there is no central point. The expansion happens everywhere. Every location sees the same behavior. Imagine points drawn on a rubber sheet. As the sheet stretches, the points move farther apart. No point is the center. All distances increase. This is how space expands. If space is expanding now, then in the past it was smaller. If we trace expansion backward, distances shrink. Eventually, everything was much closer together. This gives us a starting point, and a starting point allows an age. The universe does not expand randomly. It follows measurable rules. Scientists measure how fast galaxies recede. They compare distance and speed. From this, they determine how quickly space is expanding. Once the expansion rate is known, scientists can reverse it mathematically. They imagine the universe shrinking, slowly, evenly, until distances approach zero. The time required for this reversal corresponds to the age of the universe. This backward tracing does not point to a sudden explosion. It points to a smooth, continuous process. Space expanding, time unfolding, change accumulating. The expansion rate is measured in many independent ways. Different galaxies, different distances, different techniques. They all agree within small margins. This agreement strengthens confidence in the age estimate. Expansion turns the universe into a story. Early chapters were compact and hot. Later chapters are spacious and cool. We exist in a chapter where stars and galaxies are common. The age of the universe is the length of this story so far. As space expands, energy spreads out. The universe cools. This cooling leaves signatures that can be measured today. Temperature becomes another clock. The universe does not remember consciously, but its current state reflects its past. Expansion encodes history into space itself. There is no rush in cosmic expansion. It happens slowly, over billions of years. Nothing sudden, nothing chaotic, just steady change. Expansion does not mean collapse. It does not mean explosion. It simply describes how distances change. The universe continues. Quietly, patiently, every observer in the universe would measure expansion. No location is special. No viewpoint is privileged. This universality makes the story simple. The age of the universe is not chosen. It emerges naturally from how space behaves. The numbers come from observation, not assumption. When light travels across the universe, it does not always arrive unchanged. Over great distances, something subtle happens. The light stretches, not suddenly, not dramatically, just gently, over time. Redshift is a change in light. When light stretches, its color shifts toward the red end of the spectrum. This does not mean the light turns red. It means its wavelength becomes longer, and its energy slightly lower. This stretching carries information. Light stretches because space stretches. As the universe expands, space itself grows. And as light travels through expanding space, it is carried along, slowly stretched with it. This happens naturally. Nothing forces it. In everyday life, we associate redshift with motion. A sound changes pitch as it moves away. Light behaves similarly, but in the universe, there is more to the story. Redshift is not only about galaxies moving, it is about space expanding between us. When astronomers measure light from distant galaxies, they see a consistent pattern. Almost all distant galaxies show redshift, and the farther away a galaxy is, the greater the redshift. This pattern appears everywhere. Distance, redshift, and time are connected. More distance means light has traveled longer. Longer travel means more stretching. More stretching means greater redshift. So redshift becomes a measure of time. By measuring redshift, scientists estimate how long light has been traveling. This tells them how old the light is. And because light shows us the past, it tells us how old the universe was. When that light was emitted, galaxies closer to us show small redshifts. Galaxies farther away show larger redshifts. The most distant galaxies show extreme redshift. This gradual change forms a timeline. High redshift means early time. When we observe highly redshifted light, we are seeing the universe when it was younger, hotter, and denser. Redshift allows us to study different ages of the universe at once. Redshift is quiet. It does not announce itself. It simply appears in careful measurements, in gentle shifts of color. This quiet nature fits the universe well. When redshift measurements are combined with expansion models, they point to the same age, billions of years. Not guessed, not assumed, measured. Redshift is not used alone. It agrees with our expansion measurements, a cosmic background radiation, a star ages. When independent methods agree, confidence grows. Redshift does not point to a center. Every direction shows the same effect. This confirms that expansion is uniform. Uniform expansion supports a single cosmic beginning. Without redshift, we would not know how far back we are seeing. Redshift turns light into a timeline. It transforms observation into history. Nothing about redshift is rushed. It accumulates slowly, over billions of years. This slow change mirrors the calm nature of cosmic evolution. There is no need to hold on to details. Just remember this feeling. Light stretches, space expands, time reveals itself. As we continue gently backward in time, the universe becomes smaller. Not suddenly, not dramatically, just gradually. As space itself contracts, distances shorten, energy concentrates, everything draws closer together. In the early universe, space was much hotter, energy was packed tightly, temperature was high, but evenly distributed. There were no hot spots, no cold regions. Everything shared the same warmth. This heat was not like fire. There were no flames, no burning. Heat existed as energy, spread throughout space itself. Matter and energy were closely linked. The early universe was simple. There were no stars, no galaxies, no planets, only the most basic ingredients. This simplicity is important. Complexity comes later. Slowly, matter was packed tightly. Distances were tiny. Particles interacted constantly. Nothing traveled far without meeting something else. The universe was crowded, but calm. There were no shapes, no boundaries, no structures. Everything was nearly uniform. Small variations existed, but they were subtle. These small differences would later grow into everything we see. As the universe expanded, it cooled. Cooling allowed change. Energy slowed. Particles settled. New forms became possible. Expansion was not violent. It was steady and continuous. As expansion continued, time advanced. Moments accumulated. Processes unfolded. Nothing rushed. Everything followed simple rules. At very early times, energy dominated. As the universe cooled, energy transformed into matter. Particles appeared, persisted, and interacted. This transition marked an important stage. There was no announcement, no sound, no signal, just a gradual shift from one condition to another. This quietness is characteristic of cosmic history. Even in its earliest stages, the universe was balanced. Forces existed in harmony. Nothing overwhelmed. This balance allowed stability. The early hot universe leaves traces. These traces can still be detected today. They act as markers, pointing back to early times. By studying them, scientists infer how long the universe has been evolving. As the universe cooled, it did not forget its past. Temperature changes left signatures. Energy distributions left patterns. These patterns still exist, frozen into the cosmos. Cooling did not stop. It continues today. The universe is still expanding, still cooling, still changing. The age of the universe includes this entire cooling history. The transition from hot to cool took millions of years, then billions. Time unfolds generously. There is no hurry. Physical laws did not change. They guided every step. Consistency across time allows scientists to reconstruct the past. This consistency is key to measuring age. These early moments are difficult to imagine. That is normal. They exist far outside everyday experience. We approach them slowly, with patience. Picture a universe filled evenly with warmth, expanding gently, cooling gradually. No shapes yet, no light traveling freely, just quiet energy. Even in the deepest darkness of space, there is light. Not bright, not visible to human eyes, just a faint, gentle glow, present in every direction. This light fills the entire universe. This glow does not come from stars. It does not come from galaxies. It does not come from planets. It comes from a much earlier time, long before any of these existed. This faint glow is a memory of a time when the universe was hot, dense, and filled with energy. As the universe expanded and cooled, this energy did not disappear. It faded, it stretched, it softened. In the early universe, light could not move freely. Matter was packed too closely together. Light was constantly scattered, absorbed, and re-emitted. But as the universe cooled, a quiet transition occurred. Atoms formed, space cleared, and light was finally released. That moment marked the first time light could travel across the universe without constant interruption. That light has been traveling ever since, for nearly the entire age of the universe. After billions of years of travel, that ancient light still exists. It has cooled dramatically. It has stretched with expanding space. Today, it appears as very low-energy radiation, gentle, uniform, quiet. This glow comes from all directions. No matter where you look, it is there. This tells us something important. It tells us the early universe was nearly the same everywhere. Uniform, balanced. This ancient light is called the cosmic microwave background. It is the oldest light we can observe directly, older than stars, older than galaxies, older than planets. This light comes from a very specific time in the universe's history, a time when the universe became transparent. By measuring the properties of this light, its temperature, its distribution, its tiny variations, scientists can calculate how long ago it was released. When scientists trace this light backward, they find a consistent result. The time since its release matches the age estimated from expansion and redshift, independent clocks agreeing with one another. The cosmic background is not perfectly uniform. There are tiny variations, extremely small differences in temperature. These variations are important. They are the seeds that later grew into galaxies and clusters. These variations are incredibly subtle. They are measured in millionths of a degree. Nothing dramatic, nothing violent, just gentle unevenness. This quiet beginning fits the calm nature of cosmic evolution. These patterns have remained unchanged for billions of years. They are frozen into the background light, a snapshot of the universe when it was very young. The universe does not forget. Its past is written into radiation, into motion, into structure. The cosmic background is one of the clearest memories we have. When multiple lines of evidence agree, confidence increases. Expansion, redshift, background radiation, they all point to the same age, not approximately, remarkably precisely. Science often advances through disagreement, but here, there is agreement. Different methods, same story. A universe about 13.8 billion years old. This ancient light continues to move. It passes through galaxies. It passes through empty space. It passes through Earth and through us without notice. There is nothing loud about this discovery, nothing demanding attention. It simply exists, like the universe itself. After the first light was released, the universe entered a quieter phase. Expansion continued. Cooling continued. But now, something new was possible. Matter could finally settle. As space expanded, temperatures slowly dropped. Not suddenly, not dramatically, just gradually. Over hundreds of thousands of years, cooling opened the door to new forms of structure. At first, the universe was too hot for atoms to exist. Particles moved too quickly, but as cooling continued, electrons slowed and could finally remain attached to nuclei. Atoms formed, mostly hydrogen, with some helium. Simple, light, abundant. The formation of atoms was not explosive. There was no sound, no flash, just a gradual settling. As energy levels changed, this moment quietly transformed the universe. With atoms in place, light no longer scattered constantly. Space became transparent. Photons could travel freely. This is why the cosmic background light was released. The universe became visible. After this release of light, the universe entered a long, dark period. There were no stars yet, no galaxies, just vast regions of neutral gas, slowly drifting. This era is sometimes called the Cosmic Dark Ages. Darkness did not mean nothingness. Matter was present everywhere. Hydrogen filled space. Gravity quietly began its work. Small differences in density, left over from earlier times, started to matter. Gravity does not rush. It pulls gently, over long periods. Regions slightly denser than average attracted more matter. Over millions of years, these regions grew. Clouds of gas slowly thickened. Not quickly, not violently, just patiently. Gravity gathered material, layer by layer. This was the beginning of structure in the universe. During this quiet era, time continued to pass. Millions of years became hundreds of millions. The age of the universe grew steadily. even while little seemed to happen. The Dark Ages may feel uneventful, but they are essential. They allowed gravity to prepare the universe for what came next. Without this long pause, stars could not form. This stage marks a transition from smooth simplicity toward gentle complexity. Nothing forced, nothing sudden, just natural progression. Eventually, as gas clouds grew dense enough, something changed. Temperatures rose locally, pressure increased, and deep within these clouds, the first stars began to ignite. The formation of the first stars marked a major transition. Light returned to the universe, not faint background light, but bright, focused sources. This was the end of the Dark Ages. By studying when atoms formed and when stars appeared, scientists narrowed down the timeline. Each stage fits into a consistent sequence. Each confirms the same age. Nothing in this story is rushed. Billions of years unfold gently. The universe takes its time. Understanding it requires the same patience. After a long period of darkness, light slowly returned. Not suddenly, not everywhere at once, just here and there, in quiet pockets of space. The first stars were beginning to form. For hundreds of millions of years, the universe contained no stars at all, only gas, mostly hydrogen and helium, drifting through expanding space. This long delay is important. It shows how patient cosmic processes are. During this time, gravity never stopped. It pulled gently on gas, slightly more in some places than others, over very long periods. These differences grew. Gas clouds slowly became denser. Eventually, some gas clouds became dense enough to begin collapsing inward. Gravity pulled material toward the center. As the cloud contracted, it warmed. Pressure increased. Still, nothing dramatic, just steady change. At the center of these collapsing clouds, temperature and pressure rose high enough for nuclear reactions to begin. Hydrogen atoms fused together. Energy was released. A star was born. No fire, no explosion, just balance. The first stars were unlike most stars today. They were extremely large, very bright, and short-lived. They burned through their fuel quickly. In cosmic terms, when the first stars appeared, they changed the universe. They emitted intense light. They heated surrounding gas. They ended the long cosmic darkness. This period is sometimes called the cosmic dawn. Inside the cores of these early stars, new elements formed: carbon, oxygen, heavier atoms, elements that did not exist before. These elements would later become the building blocks of planets and life. Because the first stars were so massive, they did not live long. They burned brightly, then ended their lives. Some collapsed quietly, others released their material back into space. This enriched the surrounding gas. Later stars formed from this enriched gas. They were smaller, longer-lived, more stable. The universe was becoming more complex, but always gradually. Stars follow predictable life cycles. Their brightness, their color, their lifespan, all depend on their mass. By observing stars at different stages, scientists can estimate their ages. Some stars observed today are extremely old, nearly as old as the universe itself. Their ages provide a lower limit on how old the universe must be. The universe must be older than its oldest stars. Star ages agree with expansion measurements, redshift observations, and background radiation. Different clocks, same time. This consistency is powerful. As stars formed, they gathered into groups. Gravity pulled them together. Galaxies slowly emerged, not all at once, piece by piece. With stars and galaxies, the universe gained structure. Patterns appeared. Clusters formed. The simple early universe became richly textured, all over billions of years. Throughout all this, time continued to pass. The age of the universe grew steadily. Nothing rushed. Nothing skipped ahead. Every star you see in the night sky exists because of this long history. Their light carries the story of the universe's age. Imagine the first points of light appearing slowly, one by one, in a vast dark cosmos. Galaxies are not static. They change, slowly, over billions of years. Their shapes evolve. Their stars age. Their structures become more organized. Because of this, galaxies can be used as clocks. When we observe very distant galaxies, we see them as they were long ago. These young galaxies look irregular. They appear scattered. Their shapes are uneven. This tells us they are in early stages of development. Closer galaxies, which we see as they are now, often look smoother. They have well-defined shapes, spiral arms, central bulges. These features take time to form. Galaxies do not form fully shaped. They grow gradually. Stars are born over billions of years. Gas settles. Gravity organizes matter. This slow process reveals how much time has passed. By comparing galaxies at different distances, scientists compare galaxies at different ages. This comparison forms a timeline. Early universe. Small, chaotic galaxies. Later universe. Large, structured galaxies. Galaxies often merge. This happens slowly. Two galaxies drift closer, interact, and eventually combine. Mergers reshape galaxies. They leave visible traces. These traces tell a story of time. Galaxies contain stars of many ages. Some stars are young and bright. Others are old and dim. By studying these populations, scientists estimate how long a galaxy has been forming stars. In astronomy, elements heavier than hydrogen and helium are called metals. These elements are created in stars. Young galaxies have fewer metals. Older galaxies have more. Metal content increases over time. Across the universe, galaxies follow similar evolutionary paths. Different sizes, different environments, but the same general progression. This consistency strengthens age estimates. The ages inferred from galaxies match the ages inferred from expansion. They tell the same story. A universe that has been evolving for billions of years. Galaxy evolution is not directed. It follows gravity and physical laws. Slowly, predictably, without urgency. A galaxy's shape is a record of its history. Smooth shapes indicate long settling. Chaotic shapes indicate youth. Shape becomes memory. There is no sudden appearance of complex galaxies. Complexity emerges slowly. The age of the universe allows this to happen. Galaxies are not isolated. They exist within clusters, within filaments, within vast cosmic structures. These structures also evolve over time. On the largest scales, galaxies form patterns, web-like structures, empty voids, dense regions. These patterns take billions of years to form. Large-scale structure acts as another cosmic clock. Its current state matches a universe of known age. Again, agreement appears. Galaxy evolution is slow. Nothing dramatic. Nothing sudden. This slowness is calming. Imagine galaxies slowly shaping themselves over immense spans of time. No hurry, no pressure. Some stars in the universe are very old. Not old in a human sense, but old in a cosmic sense. They formed when the universe was still young, and they continue to shine today. These stars are quiet witnesses to deep cosmic time. If a star exists today, and we can estimate how long it has lived, then the universe must be older than that star. This simple idea makes old stars powerful tools for measuring age. They set a lower limit. The universe cannot be younger than its oldest inhabitants. The oldest stars are not found everywhere. They tend to live in special places, dense groups called star clusters, or in the outer regions of galaxies. These environments preserve ancient stars. Some of the oldest known stars reside in globular clusters. These are tightly packed spheres, containing hundreds of thousands of stars. They orbit galaxies quietly, unchanged for billions of years. Stars in a globular cluster tend to form at nearly the same time. This makes them easier to study. Their shared origin allows scientists to compare their properties and estimate their age accurately. Stars follow predictable life paths. Their brightness and color change slowly over time. By observing where stars fall along this life path, scientists can estimate how long they have been shining. One key feature is when stars begin to leave their stable phase. This turning point depends on age. In older clusters, this point appears lower and dimmer. This provides a clear age signal. When scientists study the oldest clusters, they find ages exceeding 12 billion years. These stars formed when the universe was still very young. This tells us something important. If stars are over 12 billion years old, then the universe must be older than that. This matches age estimates from expansion and background radiation. Again, different clocks agree. Star ages do not stand alone. They reinforce other measurements. When multiple methods converge, confidence grows stronger. This convergence is one of science's strengths. Ancient stars contain very few heavy elements. This is expected. Early in the universe, few stars had lived and died. Few heavy elements existed. Low metal content signals great age. As time passed, stars created heavier elements. Later stars contain more of them. By measuring this chemical makeup, scientists infer relative age. Old stars are chemically simple. Old stars are like fossils. They preserve conditions from early times. They allow us to study the past without traveling anywhere. These stars have existed through galaxy formation, through mergers, through cosmic change. They continue, unchurried, steady. Their endurance is calming. Human history spans thousands of years. These stars have existed for billions. The difference in scale can feel overwhelming, but it can also feel grounding. Stars take their time. They burn slowly. They change gradually. They do not rush. This mirrors the universe itself. Imagine a star that has been shining for nearly the entire age of the universe. Quiet, steady, patient. Much of the universe cannot be seen, not with eyes, not with telescopes, yet it is there, quietly influencing everything. This unseen presence is called dark matter. Dark matter does not glow. It does not reflect light. It does not emit radiation, but it has mass, and mass affects motion. We know dark matter exists because of what it does, not because of how it looks. Galaxies rotate too quickly to be held together by visible matter alone. Something unseen provides extra gravity. Dark matter surrounds galaxies. It forms vast halos. These halos provide stability. They hold galaxies together, gently, over billions of years. Without dark matter, the universe would look very different. Galaxies would struggle to form. Matter would disperse too easily. Dark matter quietly shaped the large-scale structure of the universe. Dark matter played an important role very early in cosmic history. Long before stars formed, dark matter gathered. It created gravitational wells. Normal matter followed. This helped structures form sooner. The timing of structure formation depends on dark matter. Models of cosmic evolution include dark matter to match observations. Without it, the timeline would not fit. when dark matter is included in models of the universe, the resulting age matches all other measurements. Again, consistency appears. Dark matter does not change much over time. It does not burn. It does not cool. It remains stable. This stability allows long-term structure. Dark matter does not rush. It does not announce itself. It simply remains, quietly shaping the cosmos. This quiet influence fits the calm rhythm of cosmic time. The distribution of dark matter around galaxies tells us about their history. Older galaxies show well-developed dark matter halos. Younger systems look less settled. On the largest scales, dark matter forms filaments. Normal matter follows these paths. Galaxies line up along them. These patterns take billions of years to form. The universe's web-like structure is a record of time. Its current shape reflects how long gravity has been working. That time matches the known age. Dark matter may sound mysterious, but its role is simple. It adds gravity. It slows change. It stabilizes structure. These effects allow the universe to evolve gently. With dark matter present, the universe evolves smoothly, without chaos, without collapse, without rush. This smooth evolution supports long timescales. Imagine an invisible framework holding galaxies in place, quietly, for billions of years. As the universe continues to expand, something subtle shapes its future. Not matter, not light, something quieter, something that works in the background. This influence is known as dark energy. Dark energy cannot be seen. It does not glow. It does not clump. It does not form structures. Yet its presence is felt through the motion of space itself. When scientists measured the expansion of the universe with increasing precision, they noticed something unexpected. Expansion is not slowing down. It is speeding up, very gently, but consistently, over billions of years. The rate at which space expands has slowly increased. Galaxies drift apart more rapidly now than they did in the distant past. This acceleration points to an underlying influence. Dark energy appears to be linked to space itself. As space expands, dark energy does not dilute. Its influence remains steady. This makes expansion continue and slowly accelerate. The age of the universe depends on how expansion changes over time. If expansion had slowed too much, the universe would appear younger. If it had accelerated too early, the timeline would not match observations. Dark energy fits perfectly into the timeline. For much of cosmic history, gravity dominated. Expansion slowed gently. Later, dark energy became more important. Acceleration began. This balance explains the universe's current age. Acceleration is not dramatic. It is not explosive. It is extremely gentle. So gentle that it took billions of years to notice. Dark energy shapes What comes next? If it remains constant, the universe will continue expanding for an unimaginably long time. Stars will fade, galaxies will drift apart, but all of this lies far in the future. The universe does not rush toward an end. It continues, patiently, quietly. Dark energy does not destroy. It simply stretches space further. The universe has an age so far, but its future age has no known limit. Time may continue indefinitely. Expansion may never stop. There is nothing violent in the universe's predicted future, just cooling, fading, increasing stillness. This calm ending matches the calm beginning. When dark energy is included in cosmic models, everything aligns. Expansion rates, star ages, background radiation. Once again, different methods agree. Science gains confidence when independent ideas converge. Dark energy helps resolve differences. It completes the story of cosmic age. Nothing about cosmic history is rushed. Even acceleration is slow. Even change is gradual. This reinforces the idea of deep, patient time. Imagine space itself, stretching quietly, carrying galaxies gently apart, without sound, without effort. Thinking about cosmic time often brings perspective. Human worries feel smaller, moments feel lighter, time feels gentler. When people learn that the universe has an age, a natural question often follows. What was there before? Before space expanded? Before time began? Before the universe existed? It is a quiet question, and a difficult one. The question feels simple, but it reaches beyond everyday experience. We are used to thinking in terms of before and after, but those ideas depend on time, and time itself is part of the universe. According to modern understanding, time did not exist independently. It began with the universe. As space expanded, time unfolded. Before that, there was no before, in the usual sense. Imagine asking, what lies north of the North Pole? The question uses familiar language, but it no longer applies. In a similar way, asking what came before time may not have meaning within our current understanding. Science is careful. It describes what can be observed, measured, and tested. When we ask about time before time, we reach the edge of what science can describe, and that is okay. Not every question needs an immediate answer. Some questions are meant to create stillness rather than resolution. This is one of them. Physics allows us to describe the universe from a very early moment, a moment when space was hot, dense, and expanding. Beyond that moment, our equations lose clarity. The story fades into uncertainty. Uncertainty is not a weakness. It is honesty. It reminds us that understanding grows slowly, over time, just like the universe itself. Some theories imagine cycles, Others imagine multiple universes. Some imagine deeper laws, yet to be discovered. But these ideas remain speculative. They are not required. To understand the universe's age, the age of the universe we measure does not depend on what came before. It depends on what we observe now. Expansion, light, structure. These tell a complete story, from the earliest observable moment onward. The beginning of the universe, as far as science can tell, was not loud, not chaotic, not violent in a human sense. It was simply a change in conditions, a moment when expansion began. Time did not start with a ticking clock. It emerged as a gradual flow, moments following moments, processes unfolding quietly. For now, it is enough to say this: the universe has an age. Time has a duration, and that duration has meaning, even without knowing what lies beyond it. There is calm in accepting uncertainty, no pressure to solve everything, no urgency to explain it all. The universe does not hurry, and neither must we. Human time is small. We count days, weeks, years. We plan ahead. We remember the past. We feel time passing. Cosmic time is different. It stretches across billions of years, quietly, patiently, without urgency. A human life lasts decades. On a cosmic scale, this is a brief moment, shorter than a blink. Yet this moment matters, because it is experienced. The universe does not measure our time. It does not hurry. It does not pause. It simply continues. And within that continuation, we exist. Earth itself is ancient, over 4 billion years old. It formed long after the universe had already existed, for billions of years. This means the universe was already mature before Earth appeared. Life emerged even later, civilization later still. This reminds us that complexity takes time, a great deal of time. The universe did not rush to create stars. It did not rush to create planets. It did not rush to create life. Everything unfolded slowly, patiently, step by step. Even though our time is short, it is still part of the universe's story. The universe is old, but it is not finished. It continues to change, and we exist within that change. When viewed against cosmic time, many worries lose weight. Moments become softer. Pressure eases. There is comfort in recognizing how large the universe truly is. The universe does not demand productivity. It does not judge pace. It simply exists, and that existence is steady, reliable, unchanging. Our time feels fast because we notice change, birth, growth, aging. Cosmic time feels slow because change is subtle. Both are real, both are valid. Human time and cosmic time are not separate. They are nested. Our moments exist inside cosmic moments. Our years exist Inside cosmic years, every atom in your body was created long ago, forged in stars, billions of years in the past. Your body is made of cosmic history. This connection brings comfort. You are not separate from the universe. You are part of it, formed from it, sustained by it. The universe holds galaxies, stars, planets, and life. It holds past and future. It holds stillness and motion. Time does not need attention. It does not need management. It flows quietly, consistently. Allow yourself to feel the scale of time without needing to understand it. Just rest within it. There is nothing left to explain, nothing to solve, nothing to remember. The story of the universe does not end here. It simply continues. Long after this moment, the universe remains, expanding quietly, cooling gently, changing slowly. It does not rush. It does not pause. Time continues, whether it is observed or not. Seconds pass, minutes drift, years follow years. The universe does not keep count. The age of the universe is not a fixed number. It grows, moment by moment, always becoming slightly older. There is no sudden change, no signal, no transition, just continuation. Breathing happens on its own, in and out, quiet, steady, no effort required. The universe holds space. Space holds galaxies. Galaxies hold stars. Stars hold planets. Everything is supported. You do not need to listen. You do not need to follow. Awareness can fade. Gently. Completely. There is no urgency. No deadline. No expectation. Time unfolds as it always has. Darkness is calm. Stillness remains. Nothing disturbs the quiet. You can rest now. Everything continues, without effort.